Okay, we're live. Gonna start the class in a second now. All right, shall we begin? Shh. Let's start. Am I mic'd? Can you hear me? I can never tell. Thank you very much. Let's play with the lights again. Worse? Is that worse? Damn. All right, cool. How about this? That's better. Okay, so as you know, your assignments are due tonight, midnight, and about 2/3 have already submitted it. Some people are having trouble finding the submit button on the Blackboard site. If you can't find the button and you're really struggling there, let me know like before this evening. So don't get these people at midnight saying, "Professor, I was done. Really, I couldn't find the upload button," because I don't find that. Yes. No, don't have a title in a specific way. Once it's uploaded to the website, it'll be held in that space just for that assignment. If you're looking for how to like format the actual things, doesn't matter. Make the TA work for a living. Make them find the answers. But the easiest thing is like a table saying, "Here's my answers." For this particular assignment, all I care about is the answer. For the next assignment, it gets harder. And after that, so in this one, obviously, I've told you exactly what to do. If you read precisely what I'm saying. For the next one, it'll be more like, here's a scenario, here's the data. You decide on the test to be applied, and you interpret that test. So baby steps. This one is pretty easy. Yes?
On my Blackboard, there's no, like, it doesn't show up to submit.
Interesting. Okay. Anybody else have that problem?
Literally just me.
No, there are two others I know for sure. So if you can't find it by, say, 2 o'clock today, email me and I'll take a look and see. Maybe you submitted something already by accident and I have to go delete that submission or something. That's happened to somebody else already. So yeah, so it shouldn't be a problem. It's, the system has flaws. And if you don't know, Blackboard Learn is an open access system, I think. No, it's not. It's a paid system. But we only have like 4 guys on campus who manage it. All right. What else was I going to say? I forgot what I was going to say. How are the t-tests going? Any problems with t-tests so far? It's one of the basic tests for continuous data that you will encounter again and again in your careers, even though, as I mentioned, it's largely out of fashion amongst professional statisticians who use what's called Bayesian methods and general linear models and things like that. But we need to know t-tests. And today we're taking the next step on the t-test evolution towards the thing that someone had asked about last class. I forgot who it was, who asked, what do we do if there are more than 2 categories to measure? So, but the thing to remember is that if you're trying to compare the means of 2 groups, a t-test is the obvious way to do so. Anytime you see means, averages that you want to compare, think t-test. T-test is also the fundament for some of the later, more complicated tests that you may do, the regressions and so forth. All right. So we looked at the t-test. We looked at comparing 2 means from 2 samples, as in, again, your stats mark versus the other class's stats mark. Are they significantly different? We looked at comparing 1 mean to an external value, as in, is your mean mark statistically equivalent to, say, 65%, right? And we looked at actually comparing the same average twice, like, is your mean mark on the midterm different from your mean mark on the final? That's actually a test I actually will do to determine if you guys have improved from the midterm to the final. So these are functional sorts of tests. What happens, though, if we want to compare the means of 3 different samples? So stats class over here, A, stats class B, stats class C. What do I do there? Is there a way I could use a t-test there? Can you see an obvious way? Knowing that a t-test only compares 2 samples, I've got 3 samples. Can you see a way I could use a t-test? No, it's basic logic. Yes? Exactly. That's exactly right. I compare these 2, then these 2, then these 2. right? But there's a better way, and that better way is something we call the ANOVA or ANOVA, depending upon who you're talking to, and that's the analysis of variance test. And ANOVAs are enormously popular among social scientists. In fact, I've rarely come across a social science presentation that didn't include ANOVAs. That's their go-to test for everything. And I say so dismissively because I find it funny to say it so dismissively. So we use it to compare group means where the t-test is inappropriate, i.e. when there are more than two groups, or when there are different dimensions to those groups. And we'll see how that looks in a second. Before I do, consider again, I've got three groups: Group A, Group B, and Group C. And maybe they've got different numbers of people in each group. Maybe it's three different, again, stat students classes. One's got 100 students, one's got 95, one's got 110, right? And each one has a mean mark on their midterms. And I'm trying to determine if they're the same or different from each other. There's a degree of variation here. How do we measure variation again? What are the terms, different things we've determined so far for measuring variability or variation? Do you remember? Variance is the big one, and variance is based on standard deviation. Exactly. And a deviation is just the distance from each mark from its mean. But here, I've got three means. I've also got a grand mean. I could add them all up and divide by whatever it's 300 students and get a grand mean. So which deviation, which variability, which variation do I care about? Do I care about how far each of you is from the mean of this class, or do I care about how far each of you is from the mean of all three classes? Or do I care about how far the mean of this class is from the super mean of all the classes? There are different ways to consider variability here. And the beauty of the ANOVA is that it attempts to incorporate all those different measurements of variability. The variability within the group, the variability between the groups. And you hear that term again and again, between group and within group differences. We call that approach the partitioning of variances, and we'll go over this in a second, but that's the strength of the ANOVA, is that it uses that approach. So the purpose of the ANOVA or ANOVA, however you want to pronounce it, is to find out whether the data from different groups have a common mean. So if we cast our minds back again to this idea of a superpopulation in which if I take a sample from a superpopulation, I'm going to get the same mean every time. So my statistical tests are really determining, is my sample from this superpopulation where the mean is such and such? Well, the ANOVA is a test to determine, are all three or all four or all five of my group of ANOVA. There's the one way, the two way, and the n way. Okay, obviously the n way is anything above 2. And what does this mean? Okay, so here's an example of a one-way ANOVA. A car company has 3 factories. Is the mean mileage of the cars produced by each factory statistically the same? So Jaguar's got a factory in India, one in Britain, and one in Spain. And we want to determine the quality of that factory output. So is the average mileage in each factory the same or different? It's only got one dependent variable, and that is which factory you're in. The independent variable is the mileage of the car. A two-way ANOVA would be something like the car factories produce 3 different models of cars in each factory. So now I've got models of cars and I've got different factories. And I care about the mileage still. So the independent variable is still the same, that's mileage. But I've got these other categories to deal with now, model and factory. So that's a two-way, 2 dependent variables. I can do an n-way. An n-way is when I got all kinds of different categories to deal with. The example here is I've got, let's say I've got factories, models, and continents, or something like that, or color of cars. So any combination of factors I can throw in, I can keep on adding more and more factors. In a real life example, it could be, my subjects could have gender, I could have which countries they live in, I could have which programs they're in, I could have which language they speak, and I'm comparing still their mean mark in stats class. So all these factors are thrown in now. Right? So obviously suddenly our analyses are getting more complicated. It allows us to look at a variety of different factors simultaneously. It's a kind of factor analysis. You probably hear that term again as well. So in this class, we're only going to do the math for a one-way ANOVA. But I want you to be aware of what a two-way and an n-way are, and I want you to be able to identify them, and if I give you the outcome, to interpret them. Much like what we did with the independent t-test, right? I don't need you to do the math, just identify it, okay? So focus again on the nitty-gritty of the one-way and just and above. So here's some examples. I'm comparing the mean bacterial count in 4 samples of milk. Which is the variable, the categorical variable, the dependent variable that I care about here? I'm comparing the mean count of bacteria in 4 samples of milk. What's the categorical variable? Okay, what's the independent variable then? The milk. Well, the bacterial sample of the milk. So the thing, the categorical variable are the different groups. The thing I'm computing the mean of is the other variable. So the way we determine whether this is a one-way, a two-way, or an n-way is the number of categorical variables. I've got one categorical variable, and that is samples of milk. Sample A, sample B, sample C. So that's a one-way ANOVA. It's got one categorical variable. Here, I've got the mean weight of men versus women among Canadians and Americans. Okay, so what's the continuous variable, first of all, that I'm measuring? It's weight. I care about the mean weight. Now, what are the categorical variables I'm measuring here? What's left over? Yes? Exactly. So gender and nationality. Okay, so those are 2 variables, 2 separate variables, gender and nationality. It's not 4 variables. It's not male, women, Canadian, American. It's 2 variables, what gender you are, what nationality you are. So that's a two-way ANOVA, 2 categorical variables. Now we've got the mean price of 6 categories of vegetables in 4 different stores in 7 different countries. Whew. All right. How many categorical variables are those, and what are they? First of all, what are we taking the mean of? What's the variable that we're computing the mean of? Price. Thank you. Yes, price. That's our continuous variable. So put that aside. So what's left over? Well, we've got the category of vegetables. We have the category of grocery store. We have the category of countries. That's 3 variables. That's a three-way ANOVA, or what we call an n-way. Right? So this is something that students sometimes struggle with. So it's defining what's a one-way, two-way versus n-way. We care about the number of categorical variables, not the number of levels in each variable, the number of categorical variables. Right? Cool. All right. And by the way, I apologize. I always confuse independent and dependent variable. I've probably done so twice already in this lecture. So the slide is correct. What comes out of my mouth is often wrong when it comes to this stuff. So the dependent variable here is the thing that you are computing the mean of. And I guarantee I'm going to get it wrong again 3 different times. So the thing you're computing the mean of, the continuous variable, that's the dependent variable. Okay? The independent variable is the thing that's categorical. So the type of ANOVA is dependent on the number of independent variables. So you're right the first time. Okay. So again, the dependent variable is always a continuous variable, interval or ratio. We can compute a mean of it. And the independent variable is either ordinal or nominal. So it's a category. So again, gender, country you live in, the province you're born in, the factory type, the sample of milk, all these different things. If you recall, the null hypothesis for the t-test was always that there's nothing going on, or equivalence. So our two samples means are the same. That's the null hypothesis. Now we've got a bunch of different samples. So the null hypothesis is the same, nothing's going on, but that they're all the same. There is a critical nuance here. We'll get to that in a second. So, but first off, if I've got 4 different samples, let's say I've got 4 different stats classes, and my question is the mean mark different or the same in these 4 different stats classes? My null hypothesis is that they're all the same. The alternative, well, this is the tricky part. The alternative isn't that they are different. The alternative is it's not the null. Why do I phrase it that way? That's a weird way to phrase it. You want to guess? Yeah?
Well, 3 of them could be the same.
Exactly right. That's exactly right. So all I can do is test if they're all the same. If one of them is different, then they're not all the same. If 2 of them are different, then they're not all the same. If 3 of them are different, then they're not all the same. I don't know which case that is. All I know is the alternative is they're not all the same. So that's a failing of the ANOVA, is that it doesn't tell us precision and resolution like that. It just tells us all the same or not all the same, not which one is different. Let's say I find out that this is true, that they are not all the same. Is there a way I could find out which one's different? Given the skills you already have, what could I do now? Yes? Exactly. I could do a t-test like this versus that versus that versus that, and this versus that versus that. So 3 to 6 t-tests. And we could do that up front, but why do 6 tests so I can do 1 and know right away if they're different or not? Okay, there are some basic assumptions, much like the t-tests when you do an ANOVA. The first is there's a random sampling from the population, and that means is you guys came to this class somewhat randomly. You probably chose one based upon the scheduling, whatever it might be, but the idea is of universal sciences students, there was an equal chance you got into this class. The dependent variable is normally distributed. So again, the continuous variable has this shape, and they usually do. That's a pretty safe assumption. And lastly, something we call the homogeneity of variances, that the variances in each of these 3 or more samples are more or less the same. Remember from the t-test, for the independent samples, 2-sample t-test, there are 2 scenarios, one in which the variances were the same and one in which there wasn't. Well, we only going to deal with a scenario where the ANOVA has a case where they're always the same, right? We can test that again with Levine statistic, much like a t-test. And the way we determine whether or not the ANOVA is robust, and by the way, robustness in statistics means this. It means that we can forget the previous assumptions if these things are in play. So robustness means that in different scenarios, the same assumptions are in play. We'll hear statisticians use robust all the time. This test is robust to sample size, meaning it gives me the same output regardless of the sample size. It's robust to distribution, meaning it gives me the same outcome regardless of the type of distribution I have. So here's how the ANOVA works. It's if the n per group, if the number of people in each group is over 20, then it's pretty much normal distribution, we can assume. We don't have to do the Kolmogorov-Smirnov test, remember that thing? Also, if the n's are different, or similar rather, so in the sense that if I have more or less of the same numbers of people in each group, then I can assume that the variances are more or less similar. These are assumptions we make to make our lives a bit easier. Whereas remember the t-test, we have Levine's test, we have the Kolmogorov-Smirnov, we have these scenarios here. So as I mentioned, the key concept with the ANOVA is this thing called partitioning of variance. And that's the idea, that's the idea that we have different groups, and within each group, there's a difference from the mean, and between each groups, there's a difference from the grand mean. Okay, so we have to account for both of those kinds of variances when dealing with the ANOVA. And the conceptual reason for this is that we try to isolate the reason for which your mark, for example, might be different from the grand mark shared by all three stats classes. So some of the reasons could be, let's say we're comparing the three different stats classes, class A, class B, and class C, and 2381 for your midterm scores. And we have a grand mean for all 300 students. So your mark may be different from the grand mean for a number of reasons. One, maybe you guys are different from each other. You're just individual variation. You didn't study as hard as that person. You studied harder. You got a background that's different. Who knows? Or it could be that each professor in each class taught it differently, better or worse. So there are factors here that relate to your variability within your group and factors that relate to the variability between each class. So we try to account for that variability in what we're going to do next. Go. Within each group is variation, and between each group is variation, so I'm saying here. So the between group variance is when we compare the differences between the group, and within group variance, we compare within the group. So again, using the classroom example, within the group, I care about how you compare to each other. Between the groups, I compare about what are the characteristics between each classes that are different. Excuse me. Right, as I mentioned, we begin this by computing a grand mean, and we're going to compute a statistic. Much like the t-test, we computed the t-statistic, and we compare that to the back of the book. We're going to compute a statistic here again, and that statistic is called the F statistic, as opposed to the t statistic. So you've learned about the Z, you've learned about the T, and now you're going to learn about the F. And the F is very similar to the T. In fact, you've seen the F already. It's actually Levine's F test, which was a test for whether or not the variances in our t-test samples were the same or different, was a variation of the t-test. The F distribution is actually just the square of the t, how it's distributed. That doesn't affect you at all, doesn't affect how you interpret things, doesn't affect the math that you do. Just be aware that there is a relationship between the t distribution and the F distribution. That doesn't mean you can just look up the t table and square it. It means the derivations are based upon the square. So it's also called the F ratio, the F statistic. So you may come across that in the textbook, F ratio. And all it is the ratio of the between group variance divided by the within group variance. So we are going to compute this in every example that we do and look this up in the back of the book to see what the p-value is. Because ultimately that's all we ever do in parametric stats is we compute our external statistic and we look up the value in the back of the book to see where it lies on the super distribution. Is it in that rejection zone or is it in the middle? Is it bigger or lower than alpha? That's all we care about. Another way to think about the F ratio, it's the effect of the independent variable. So yeah, it doesn't matter. That's complicated. Okay. We have to know about the degrees of freedom as well. Remember I mentioned degrees of freedom a couple times? Degrees of freedom is, I'll say it again, is just a way to determine the amount of play there is in our math. The number of factors that can go up and down that determine what the possible outcome might be. So if you remember in the t statistic, depending upon which scenario you're dealing with, we computed the degrees of freedom differently. So at the 1 sample, the degrees of freedom was n minus 1. For the 2 sample, it depended on if it was dependent or independent. For the dependent, I think it was the number of pairs of individuals minus 1. And for the independent, it was the total number of people minus 2. Well, we're going to compute degrees of freedom here differently again. So you have to keep it straight in your head which scenario you're dealing with to compute the degrees of freedom. So once we do that, and once we compute our F statistic, we go to page 413 and look up our p-value. So here are the formulas for degrees of freedom. We care about the degrees of freedom between the groups and within the groups. So with ANOVA, we compute 2 degrees of freedom. Okay, so degrees of freedom between the groups is the number of nominal categories minus 1. So in the case of comparing the mean mark of 3 stats classes. How many categories are there of stats class? 1, 2, 3. 3 minus 1 is 2, right? So that would be a 2 there. For the within group degrees of freedom, we care about the total number of subjects minus the number of categories. So if I've got 300 students, 3 categories, that's 297. We'll run through an example to make it clear. So, oh, you can't see that color, right? So if K is the number of categories, K minus 1 is our between group degrees of freedom, and N is always our total number of samples, total number of subjects rather. So within group, it's N minus K. All right. Here's an example. We have 4 different classes. So yes.
Sorry, is the total number of subjects all
Yes.
together?
Yes, that's right. So the example we're going to work through are 4 different classes. Let's call them stats classes. And there are 100 people in each class. That means 400 people total. So the K is going to be 4 different classes. And the N is going to be 400. That was the question. So that's going to be K minus 1, so 3. And that's going to be 400 minus K, or 397. 396, rather. There goes my math. Okay, so far, so good. Elementary school stuff so far. Really, the ANOVA comes down to memorizing a bunch of formulas and plugging them in. But the other nuance is figuring out which ANOVA applies to which criterion, which scenario. Right, so okay, so if I go to the back of the book and I look up the degrees of freedom for these numbers, I get F equals 2.60 at the alpha of 0.05, which means that's my target. That's the F that I'm going to try to compare my F to. Now I've got to compute my F. So I'm going to reject the null if the F from the table is less than the F that I'm calculating. I want my F to be bigger than the table F. Again, I always forget this. I always got to look back, see which one's bigger. I'm saying it right now. If my F is bigger than the book's F, then we have statistical significance. We can reject the null. So you can look up stuff online too. I've got a couple of online calculators if you want to use these instead. To compute our F, we have a couple new concepts. This thing called the sum of squares we have to think about. So the sum of squares is the sum of squared deviations. What's the deviation again? Who remembers? When we talk about the standard deviation, what's a deviation? Yeah. Yeah. Exactly, the distance from the mean is how much you've deviated from the mean. Exactly right. Okay, so and a standard deviation is the average deviation of sample. So we're going to square the deviations now and sum them up. Now we have 2 different scenarios. Remember, we have the deviation scenario within the one class, and we have a deviation scenario between the variety of classes. So again, much like we had 2 degrees of freedom, we're going to have 2 sets of sum squares of deviations. And our F is just the ratio of the sum squares of deviations divided by the degrees of freedom. Whew, yeah, it's a lot. If it's confusing now, hopefully the example will make it a bit clear. Okay, so I said that already. So another way to think about the sum squares divided by the degrees of freedom is to call them mean squares. So there's actually a term called the mean squares within and the mean squares between. MS sub W, MS sub B, right? And this is the formula for F. And F is just MS sub B divided by MS sub W. And that's just the sum of squares divided by degrees of freedom, and sum of squares divided by degrees of freedom. That's all it is. We just have a short form for it. That's MSB and MSW. Okay, and again, if that ratio is bigger than the table's F value, then we have statistical significance. So here's an example. This is from a textbook directly. We have randomly assigned 15 infarct patients. What's an infarct? Anyone know? Myocardial infarct? Thank you. Heart attack. Patients to one of 3 different therapies. Some are going to receive music therapy, some are going to receive relaxation therapy, and some are going to go to a control group who get no therapy at all. So group 1 is music, group 2, relaxation, group 3 is control. And after each therapy, we see how much stress they report on a scale of 0 to 10. Okay, so first of all, is this a one-way ANOVA, a two-way ANOVA, or an N-way, and why? Well, let's break it down. Yes? No. See, and I'm glad you said that, because it's important to break down these assumptions. So remember, the way we define which type of ANOVA it is by looking at the number of categorical variables. So how many categorical variables do we have? Yes?
Would it be a two-way, like for stress?
No, we're getting there closer. Is there a hand here? Yes? Exactly right. So this is the nuance that's important to grasp here. Stress is our continuous variable. That doesn't come into our definition of ANOVA. The categorical variable, there is but one, and that is which group you're in, i.e. the type of therapy. Do not mistake the levels of your categorical variable, the categories, for the variable itself. It's like saying, if you're male versus female, how many variables is that? That's one variable, gender. Okay, so here, there's one variable, that's stress group, or sorry, therapy group. Happens to have 3 levels, but there's one variable. So that is, yes?
But aren't we going to be comparing the groups to each other?
Yes.
Then that becomes
No, it's still a one-way because we're only comparing one variable across the domain of one categorical variable. The categorical variable has 3 components to it. It's kind of like, which statistics class are you in? One of 3 classes, but statistics class is the variable. See? Right. But I know it's a bit of a transitional way of thinking, because to be honest, you could think about it as being 3 variables. I could be in stats class A, yes or no, class B, yes or no, stats class C, yes or no. That's not what we're doing. Stats class.
It would be a three-way ANOVA if there's only one group and everyone in the group would be exposed to 3 different therapies.
No, it would be a 3-way ANOVA if there are 3 different categorical variables. Like, if we cared about stress level in across which therapy group you're in, which gender you happen to be, and which country you happen to be born in.
Don't two other therapies act as gender and nationality?
I'm sorry, say it again. Which?
So can't the 2 other therapies, can't they replace something and nationality?
They could, if that's the question you're asking, but then it's in one domain again. The conceptual idea of ANOVA is you've got these different dimensions here. I care about how different people are dealing with the different therapy groups, but also within that difference are the men and women doing differently in each group. And within that difference are the different Americans versus Canadians doing better. So this is why I can say Canadian women in therapy group 1 are doing this much better than American men in group 2.
Oh, okay.
See?
You have to say, like, people who have taken music therapy, how are they handling relaxation therapy, and how are they handling the third one there? Exactly
right. So it's difficult to think about anything beyond one-way ANOVA, which is why I only have the class 2 one-ways, because beyond that, it's multidimensional thinking almost. So thinking about 4th or 5th dimension. Okay. So again, the easiest way to remember this, we're looking for rote memorization, is the number of categorical variables, not the number of levels in each category, the number of categorical variables. All right. So hopefully as more examples come forth, it'll be clear. I'm glad these are coming up now, because these are the things that people will struggle with at homework time. Okay. So we want to know if the mean stress of individuals in the groups are different from each other or not. Right. So here is it. What kind of analysis? This is a one-way ANOVA, because there's one categorical variable, and that is which therapy group you are in. Right. What's the null hypothesis going to be? Thank you very much. The means are all the same. Okay. And the alternative is going to be that they're not. Okay. And again, we can't know which one is different, only if they're all the same or not. Okay. So what are K and N? K is the number of levels in our categorical variable, right? So we have one categorical variable, that is therapy group, and there are 3 groups. in that categorical variable. So K is going to be 3. And we already said there are 15 total subjects. Okay, so the degrees of freedom between groups is K minus 1, which is 2. The degrees of freedom within the group is going to be the total number of people minus K, which is 15 minus 3, which is 12. All right, so we're halfway there. So, and these are our data. The spreadsheet again. You can't see the headings again. This is music. This is relaxation. This is control. I don't know why that doesn't come up. All right, so individuals have these scores on their stresses. I sum them all up, and I take the mean of each group. So this is kind of like your stats class. Let's say this is stats class 1, stats class 2, stats class 3. But this is not. This is music group, relaxation group, control group. Here are the mean scores. This guy's obviously doing much more stressed out. The control group is much more stressed out. The music group is a little stressed, but the relaxation group is really not stressed. So I've got the means. I'm also going to compute something called the grand mean. And the grand mean is the mean of everybody together. Right? So where's that? That's 4. So if I add up everyone together and divide by the total, I get 4. Or if I add up just the means and divide by 3, I'll also get 4. They're mathematically the same process. Obviously, it's easier to just mean these 3. So we need all 4 of these numbers. We need the means and we need the grand mean. So summary again, grand mean is 4. Okay. So this is how I'm trying to bring it back to the conceptual aspects of it again. So the first guy, where's the first guy here? Group 1. He deviates from his mean by 3 points. He has 0 stress. The mean is 3. So his deviation is 3. His square deviation is going to be 9. Okay. His group 3 deviates from the grand mean by 1 or minus 1, whatever it might be. Okay. So the total variation is going to be his deviation from his group mean plus his deviation from the whole group mean. You start to see how it matters how different you are both from your group and from the overall group. Right? So if we start to compute the same thing for everyone, we start to see a splay of how everyone is spread out across the entire system. And that's what the ANOVA tries to do, is tries to determine, is everyone splayed out so much that in fact there's no similarities, or are they splayed in such a way that there's groupings here that make sense? Okay, that's how we get the F conceptually. All right, so, oh, you can't really see that heading either. Darn, all right. So this is the mean from each group. Group 1, group 2, group 3. This is the deviation of each mean from the grand mean. And this is this number squared. And this is the number of people in each group. All right? You have that in your slide, hopefully. I don't know why it's not popping up here. It's really frustrating. Okay, so right now we're computing the sum of squares just for the between group scenario. So deviations from the grand mean, square them, then we add them all up. That's it. That's the sum of squares between groups, 70. Now, this is within groups. We have 3 groups. Okay, here are each of the, here's group 1, for example. The mean of group 1 is 3. Here is the first guy, scored 0. So he's minus 3 from the mean. I square that and I get that. The second guy scored 6. He's 3 points from the mean. I square that and I get 9. The third guy scored 2. He's 1 point from the mean. I square that and I get 1. I add them all up. I do this every time here. All right. Then 10, 20. That's right. And I get that as the total number. I divide by degrees of freedom, and I get that number, 9.13. It's just rote mechanics at that point, plugging in the numbers and computing my F. I use my F there. I compare it to the back of the book, and I get, remember 2.6 was the number there, or 3.88? 3.88. Is mine bigger or smaller than the book's? Mine is bigger, yes. So therefore, thank you very much, reject the null, right? And what do I conclude? I always answer the question. What was the original question? What was my null hypothesis? That all the group means are the same. Group means of what? The group means of the mean stress of the 3 different therapy groups. I conclude that the mean stress of the 3 therapy groups are not the same. I can't say which one is more, even though I know that the control group is more. Yes?
Didn't we figure out that the means were all different a long time ago? Why did we have to compute that?
Because we know that the means are different. We don't know if they're statistically different. See what I mean? So for example, I can ask you your age, and the guy next to you, his age, you're probably like 21, he's probably 21 and a half. You're different. But are you statistically different given the context of this whole? And what I mean by that is there enough play in the distribution of ages that the difference between your 2 ages is extreme or small, depending upon the variation in the group? Okay, so it depends on the group again. So it goes back to that idea of a superpopulation. If the superpopulation of second-year students, the average mark is 21, and I've chosen you 2 guys as my samples, did you come from the same supergroup? If you did, then your ages are exactly 21. Even though they're not, they're on average 21. If in fact they're from different groups, then they're not the same average. That's what the statistics tries to tell us.
So you technically have 3 different means.
Yeah.
They're different, but they're so close together that when you compute F, it's actually less than your alpha. And so
Right. So there's a 95% chance they came from that universe where all 3 are the same. Right. And again, it comes down to the variability. If there wasn't a lot of variability, chances are that those 3 different means are quite different. But because there is so much variability, that they overlap so much that we cannot confidently say that this is representative of a difference in experience. That's what it comes down to, representativeness. That's why in that first day we talked about if I pluck this sample from the overall universe and I do stuff to it and I compute statistics, is it representative of the parameter? Right? So that's a good question. This is why we spend so much time dealing with variability and variance, because the degree of variability determines how much your actual computed mean is representative of the experience of the group. That make sense? Cool, thanks, that was a good question. Right. So to answer this question here, because we reject the null, we conclude that statistically, at the 95% level, the means of the groups are in fact different. Okay. So what we include tells us that the means are different. I said that. We can't conclude that each one is different, only that one of them is probably different. I just said that. How can we test if any one mean is different from the other means? We've already answered that twice. We do a t-test. We could do that to the we can do the music group versus the relaxation group, and the relaxation group versus control, then the music versus control, to see which one has the different relationship. So this is the way that SPSS does the output for ANOVA. It gives you, between groups and within groups, it gives you the sum of squares and the degrees of freedom. It computes the mean squares. That divided by that should be that. That divided by that should be that. It computes the F, it looks it up for you, and tells you what the p-value is. So here, that's significant because it's less than 0.05. Right? So that's why we prefer the computer to do it, because it's so much easier. And when you do it, it'll be the same thing. So that's how you read the output for SPSS. Different packages will give you different styles of outputs, but in general, they should all give you the same information, such that you can compute it yourself if you wanted to. So there's something called the repeated measures ANOVA. And it's kind of like the dependent group t-test. I mentioned that in the t-test scenario in which I'm testing your mean midterm mark versus your mean final mark to see if in fact there was a difference, improvement maybe, or maybe it got worse, I don't know. I'm testing you twice. That's a repeated measure. In statistics, repeated measures are a kind of a special problem because it introduces new kinds of error. If I measure you over and over again, I'm introducing a special kind of bias in your behaviors. So in ANOVA, if I do the same test 3 times. Let's say I'm looking to see if this group, how you do on all 3 midterms. Let's say there are 3 midterms. Midterm in September, one in November, one in December. I've tested you 3 times. The means of 3 groups, that's automatically an ANOVA, but I'm testing the same group 3 times. That's a repeated measures ANOVA. It's a special case. We have a way of dealing with it. We won't be dealing with it in this class, but I want you to know when it is and when to use it. So I can say, hey, here's a scenario in which I'm testing, again, a class 3 times. I want to see if their mean mark has changed the 3rd time. What's the test I would use? You would say a repeated measures ANOVA. But I will not ask you to compute it because who wants to do the hard math, right? And the important part of this class isn't knowing how to do the math, it's knowing what to do. Then you hire a statistician to do it. So the last couple of slides, I just show you how to do it in SPSS. You'll play with this when you come back. Is that a hand? Yeah. Well, when you play with it, you come back. And then there is a little bit of homework. Try those 2 questions and try it out. Any questions? That was a fast lecture. Yeah? Basic stuff. ANOVA is not hard. It's just mechanical stuff. It's the concept of it. The hardest part is remembering we're dealing with a number of categories. Yes? Oh, and the midterm, when is the midterm? Is it the first class back? It's the Friday. Okay, we'll have at least 1 class back. All right, that's good. We'll have a lot of review. The first class back will be all review for the midterm. I don't remember. Remind me, email me, and over the break, I will actually answer that on the website. Yes. Yes, more review questions. Email me, remind me. Okay. Thank you. And don't forget your things due. Yes. I don't remember. I remember in your finals, I gave you a cheat sheet for the last previous years. I don't remember what you did for the midterm. Again, email me. I will put all this on the website this week. Bye.